Now we're going to move into a somewhat new topic and talk about congruence of integers and congruence classes. So we're first going to review the definition of congruence, which we saw a couple of investigations ago. Given a particular congruence relation, we'll define what it means to be a congruent class. And then we'll discuss how to describe a particular congruence class. All right, so just to remind you, I like to use the model of days of the week to understand congruence. And that says that A is congruent to B mod n, means that if you have n days in the week, then A and B represent the same day of the week. So as an example, we know that 5 is congruent to 11 mod 3 because there are 3 days in a week, and between 5 and 11 there are 6 days. The difference is 6. And that is exactly 2 weeks, and therefore 5 and 11 are the same day of the week, and so they're congruent mod 3. So there are 4 different ways, at least 4. There's actually a 5th one that I'm not going to write down, but there are 4 different ways that we're going to talk about precisely defining what it means mathematically. All right, so if n is an integer, or if n is a natural number and a and b are integers, we say that a is congruent to b mod n if one of these things happens. We could say that a is equal to b plus nk for some integer k, and if that doesn't, that's hard to link with the days of the week. The k represents the number of weeks between a and b. So if k is the number of weeks, n times k is the number of days, that says that b and a are k weeks away from one another. It can work the other way around too. B is equal to a plus nk. Again, k is the number of weeks, but it might have the opposite sign depending on whether a is smaller or b is smaller. If we take that second equation and subtract a from both sides, you can see that n divides b minus a. And if we take the first equation and subtract b from both sides, you can see that n divides a minus b. So all 4 of those are logically equivalent. They're exactly the same. They're exactly equivalent to a being congruent to b mod n. So now that we've sort of understand how congruence works, it turns out that it's helpful to put them into congruence, what are called congruence classes. And to understand that, think of congruence modulo n being like a team relationship. Right? Congruence itself is a relation. That means it describes relationships between numbers. So I want you to think of it as a team relationship. So the model we're going to use, I call it the team model. So if A is congruent to B mod n, we can think of A and B being on the same team. So the test for being on the same team, check if they're congruent mod n. If they are, they're on the same team. If they're not, they're not. A congruence class is a complete set of numbers that are on the same team. So we look at all the possible ways that we can get everybody on the same team in a group, and then that's what the congruence class is. And if that sounds familiar, that's just a very wordy way of describing the team itself. So the congruence class is literally the team. A congruent to B is a relationship describing when 2 players are on the same team, and when you have that kind of relation, then you can actually describe what the teams are. That's the congruence classes. So let's see if we can give a mathematically precise way of defining them. The models are great for understanding stuff, but we need precise definitions in order to do math. So for our definition, we're going to let n be a natural number. A congruence class modulo n is a set of integers such that if 2 numbers a and b are in S, then they are congruent to b mod n. If you have 2 numbers in the same congruence class, they should be on the same team. Right? A congruent to B means they're on the same team. In other words, all the elements of S are related to each other by that relation. Right? They're on the same team. All integers not in S are not related to any elements of S. And what that means is if you take any integer, all the integers that are related to elements of S are completely included in S. You have a complete team of elements that are related. That's a perfectly good way of describing it. It's mathematically precise, but there's another way you can describe it too, right? Or at least intuitively. We'll put some mathematical substance to that in a little bit. But one thing you can do is say, hey, I'm going to choose a random team member to represent the team. You can think of it as, I don't know, A could be like the team captain. And it doesn't matter who you choose. The team, whoever you choose as team captain, it's the same team, so it shouldn't make any difference. And then what you do is you just describe the team as a set of everyone who is on the same team as A. So you pick your captain A, ask yourself who's on the same team as A, everybody gathers together, that should be your team. And we actually use this method to describe congruence classes as well. So if n is a natural number and A is an integer, so A is going to be the team captain. The congruence class of A modulo n is denoted by bracket A n. And remember, this is a team, so this is going to be a set of numbers. And it's going to be defined as follows. So bracket A sub n is equal to the set of all x in z, all integers x, such that x is congruent to A mod n. And if we say that in terms of the team model, we're looking at all integers x, such that x is on the same team as A. All right, so let's see if we can describe the congruence class modulo 3 that has a team captain 5. It contains the element 5. So we want all the integers x such that x is congruent to 5 mod 3, and let's see if we can fill up that set with numbers. So let's see, we'll start with, 5 is an easy way to start. 5 is congruent to 5 mod 3, so that's going to be on the team, right? 8 is also congruent to 5 since it's 3 away from 5. 11 is 6 away from 5. 14 is 9 away from 5. So that's all. Those are all multiple of 3 away from 5. And you can see every time you go up by 3, you also get a new one that's congruent to 5 mod 3. And you just sort of keep on going. Of course, we can do that backwards as well, right? If we go 5 back to 2. Oops, wrong way. If we go 5 back to 2, 2 is congruent to 5 mod 3. So that one works. So it's -1, -4, etc. Now you go back by multiples of 3, that also works. And one way of describing this, if we want to describe it in set builder notation, it's the set of all integers x such that x is equal to 5 plus 3k, where k itself is an integer. Right? And you had a positive multiples of k if you're bigger than 5, and you'd have negative values of k if you're smaller than 5. So the question we asked, though, is it looks like we got everybody on the team, right? So is bracket 5 truly a congruence class? Well, we got to ask ourselves a couple of questions about that, right? First, we know all the integers in bracket 5 base 3, sub 3 that we looked at up there, they're all related to 5, right? The -4, the -1, 2, 5, 8, 11, 14, those are all related to 5. But remember, to be a congruence class, they all have to be related to each other. Are they? And how would we prove that? Are all the members of the team included in bracket 5? In other words, we've got a lot of numbers that are congruent to 5, and presumably we've done the first bullet, so we've proven that they're congruent to each other. Are there any other integers that we're leaving out of our list? And just in general, some more issues that we're going to resolve just generally about bracket A sub n. Once we have that they are the congruence classes, once we've been able to find them and verify that they're actually the entire team and they're all related to each other, we have some additional questions to ask about these congruence classes as well. Is it possible for a number in the in bracket A sub n, I said A, but it could be any other member of the team, to be part of 2 different congruence classes? It's on one congruence class, bracket A, but logically, it could possibly be on another team as well. Is that possible, or can we prove that it's impossible? And the other thing is, are there any integers out there that aren't a part of any congruence classes? We have all these congruence classes, all these teams around. Is there any integer that's not a part of any of the teams? And if we have 2 congruence classes, or we think we have 2 congruence classes that happen to be represented by different integers, well, how do we tell whether or not they are actually the same equivalence class? Because it could be that they're 2 different equivalence classes. It could be that they're just the same equivalence class represented by different numbers in that equivalence class. If I take the same team and switch the team captains, that gives me the same equivalence class. How can I test whether or not that actually happens between 2 congruence classes? So now I think you're ready to work on the activities for properties of congruence on the PDF file included with this video. After that, I encourage you to watch the video called Properties of Congruence Classes. That's going to give you some more general results. That's going to give you some proofs of the general results of the problems in those in-class activities.